you seen those videos of people charging their phones with lemons?
Oh, this is a potato, by the way, but no way you could charge your phone with a lemon?
Yeah, you use some chemistry concepts and some physics concepts.
Can you please explain further?
Yeah, you use the chemistry concept of electrochemistry and the physics concept of circuits.
Wait, so why can't I just use a battery? How does a lemon help?
Well, they're acidic, so.
Oh, so it aids with the transfer of electrons.
Yeah, actually, the nail acts as the anode and the penny acts as the cathode for the transfer of electrons.
Oh, so I can use just one lemon and it'll charge my phone?
No, probably not. You need at least 5 volts to be able to charge your phone, and these can't generate that much. So you'd have to arrange them in some sort of sequence. But yeah, you had enough.
Oh, you're right. So I can charge my phone overnight?
No, these can't hold a charge for very long, but they can hold it for a little bit of time. And that's actually what we're gonna see how long.
That sounds
You know
cool.
what? Let's try potatoes instead. Lemons are boring, everyone does lemons.
I'm down.
Nice.
So the method we've decided to test is producing a current with fruit. Generally, this is only done with lemons, as you can see on YouTube. However, this time we're going to test this using a potato instead in different circuits to not only see which one works, but which one gives the most power and has the longest duration. So foods that usually produce electricity are the ones that are high in acidity and potassium, and those are the ones that have the greatest ability to do so. So to actually investigate this, what we're going to do is that we're going to take this potato and cut it in half. So using this knife here, we're going to cut this in half and we yield this. So as mentioned before, we're going to use the concept of electrochemistry. So electrochemistry pretty much yields the exchange of electrons to create an electric current. So for that to happen, you need an anode and a cathode. So an anode is what gives away electrons, and the cathode is what accepts electrons. So we're going to have two metals act as the anode and cathode. As the anode, we're going to have a galvanized nail, which is coated in zinc, and for our cathode, we're going to use a penny, which is covered in copper. So pretty much putting them into the potato like this on different terminals, we're able to create a flow of electrons and create electricity going through this using the electrolyte or salt bridge that's present inside, which is potassium. So now what we're going to do is going forward is that we're going to use different types of these alligator clips, and we're going to use this voltage meter so that we can find the voltage not only outputted by this potato by itself, but also the circuit as a whole. Okay, so approximately, as you can see, the amount of voltage within a potato is about 0.55, 0.56.
So as a comparison, we are looking at the voltage of the battery, and it seems to be staying around 1.55, which is about 3 times what we had from the potato. So in order to compensate for that, we would need to use 3 potatoes for each battery. And that seems to be how we would charge our phones, to use a lot more potatoes than we would use batteries.
Alright, so right now we put 2 batteries in a series, and the voltage reading is showing around 3, which is what it should be considering each one is a 1.5 volt battery. And we're gonna compare this to 2 potatoes in the series.
Alright, now we're testing 2 potatoes in a series to see how that compares to the batteries. And we're getting a reading of about 0.82, which isn't quite twice the amount as one single potato, but it is a significant amount more. So that's good. Now we have the 2 potatoes in a parallel circuit, and the reading comes out to be about 0.1, 0.09. So the better way to go if we want to get the maximum voltage would be to connect them in a series.
Okay, so now we're going to be testing the batteries in parallel. So here we have the batteries set up within a parallel circuit configuration. So by touching the end of these to the end of the circuit, we find that the voltage is about 0.242. So in comparison to our other values for the potato circuits, for both the parallel and and the series circuit, it can be seen that the voltages of the batteries are obviously much greater than the potatoes.
Alright, so right now we have a complex circuit with these two batteries in this parallel, and this battery is in a series in comparison to these two batteries. And looking at the voltmeter reading, we have a voltage of 2.15, and we're going to compare this value to the same setup but with potatoes.
So we reconfigured the same complex circuit we made with the batteries, but this time we used the potatoes. And now we get a reading of 0.085. So still not as good as the series. So in order to charge the cell phone, I think we're just going to stick with the series. That seems like what produces the most voltage. So what we're doing here is we cut 5 potatoes in half, so it gives us 10 half potatoes. And we're setting them all up in a series because in the trials that we ran earlier, we found that hooking them up in a series gives us the maximum voltage. So we're thinking that since we got about 0.5 for 1 half potato, if we get about 10 in a series, it should add up to about 5 volts. And we're gonna see if that'll work to charge our phone.
So as you can see here, we pretty much as determined before that the series was the best option for us to charge our phone. So here we have the potato set up in a series, and here as you can see, we're going to test the voltage, and we have about 5.7, 5.6 volts. So pretty much this is how much we hypothesize, a bit more than how much we hypothesize and how much we need to actually charge our phone. So if we do the same thing and touch the sides of this to the car charger, similar to how a car works, the car battery, we should be able to charge our phones. However, as you can see, the phone does not charge.
Here it goes. So here we have all the circuit diagrams drawn out. The first one would be a simple circuit, which would just be one voltage source and one resistor. And here we have the Kirchhoff laws. Then would be the series, which would be 2 voltage sources right next to each other, and then the 1 resistor. Here we have the parallel circuit, which would be the 2 voltage sources in parallel, and then there's the resistor. And then here we have the complex circuit with the 2 in a series and then 1 parallel to them with the resistor at the end. And we found that the average power coming from 1 potato would be 0.8. So that makes the current 1.6 since the voltage coming from 1 potato would be 0.5.
So we had an initial reading of 5.8 volts around. So I'm gonna plug this USB into the iPhone, and as you can see, it's not clearly charging it. But after around 5 minutes, with it still plugged in, we're gonna unplug it and see how much voltage we lost. And if there's a loss in voltage, that will clearly tell us that it used voltage into charging the iPhone, but it just wasn't enough to actually charge. But it put energy in to try to charge it. Alright, so now it's been around 10 minutes, and we're checking the voltage reading now. And it went down from 5.2 to 5.1 around. So it went down around 0.01. So as we can see, when it went from the first 5 minutes, it went down from 5.8 to around 5.2, which is quite a big difference. But then the next 5 minutes, it only went down from 5.2 to 5.1. So this shows an exponential relationship when decreasing and when discharging. So that means that it will still, so that means this this voltage source will last for around a couple hours, will be very low, and it won't be anywhere close to as efficient as the actual battery.
So the main purpose of this experiment was so we can see if we could charge our phones with the potatoes. However, our phone wasn't able to be charged. So one thing that we found was that if we maybe increase the amount of potatoes that were feasible, maybe to 4 times the amount of potatoes that we have here, we might be able to charge our phones. Or if we increase the electrons traveling through due to electrochemistry, if we increase the amount of nails and the amount of copper pennies, maybe that would have created a higher voltage. However, for us, we didn't get that. So we pretty much conclude that you're not able to charge your phone with a certain amount of potatoes. But if you would like to, you'd have to increase the amount of potatoes within that respect.
So our sources of error, since we did create enough voltage to charge a phone, but it didn't actually end up charging, our sources of error could have been somewhere in the circuitry of the potatoes. We could have wired them wrong, and maybe if you wire them differently it would have worked. Or it could have been in the part of the charger that we plugged the cords into, or just how we plugged the cords in. We really don't know where the source of error was, but according to the readings, we should have been able to charge the phone. So what we can conclude is that potatoes don't work as well as batteries as we kind of expected. Hey, have you seen those videos of people charging their phones with lemons?
With lemons? No way. But this is a potato. Fuck, I fucking. So right now